In this video, we tackle more examples to familiarize you on how to work on the explicit formula of arithmetic sequence. Welcome to Mathematics of Engineering. The first example has an arithmetic sequence which involves 3, 15, 27, and 39. The task asks for the term which is 216 more than the 63rd term of the sequence. So having the first terms, we can identify the common difference, which is 12. Then, from the explicit formula, we solve for the 63rd term. So a sub 63 is equal to a sub 1 plus the common difference d multiplied by the quantity n minus 1. So plugging the available values, we have a sub 63 is 3 plus 12 multiplied by the quantity 63 minus 1. Simplifying the value in the parentheses, we get a sub 63 is equal to 3 plus 12 times 62, or that is taken as a sub 63 is equal to 747. Now that we know the 63rd term, we add 216 as is stated in the problem to have 963. This is taken as a sub n. Since we are looking for the term n, we plug 963 into the explicit formula and equal this to 3 plus 12 times the quantity of n minus 1. Now distribute 12 to eliminate the parentheses, and we end with 963 is equal to 3 plus 12n minus 12. So collecting all terms, we have 963 is equal to 12n minus 9. Then, transpose negative 9 to the other side of the equation to have 12n is equal to 972. Finally, isolate n by dividing everything by 12 to get n is equal to 81. Example 2 states, how many multiples of 6 lie between 20 and 250? Between 20 and 250, the multiple of 6 closest to 20 is 24. We consider this as a sub 1. Likewise with the multiple of 6 closest to 250, which is 246. Treat this as the final term or a sub n. With the help of the explicit formula, plug a sub 1 and a sub n to get 246 is equal to 24 plus 6 times the quantity of n minus 1. Again, take the parentheses out by distributing 6 to have 246 is equal to 24 plus 6n minus 6. Collect all constants to arrive at 246 is equal to 18 plus 6n. Then transpose 18 to the other side to have 228 is equal to 6n. Isolate n by dividing the equation by 6 to have n is equal to 38. Therefore, there are 38 multiples of 6 between 20 and 250. Example 3 does not provide a sequence, and it states the sum of the fourth and eighth terms of an arithmetic sequence is 24. Likewise, 44 is the sum of the sixth and 10th terms. Determine the first three terms of the pattern. With limited values given, we utilize the explicit formula to limit the unknowns. First, we convert a sub 4 to a sub 1 plus d multiplied by 4 less 1, or that is a sub 1 plus 3d. Do the same with a sub 8, which is equated to a sub 1 plus d times the quantity of 8 minus 1, simplified as a sub 1 plus 7d. The problem states that a sub 4 and a sub 8 are equal to 24. This we can expand as a sub 1 plus 3d plus a sub 1 plus 7d is equal to 24. Collect similar terms to get 2 a sub 1 plus 10d is equal to 24. Take this as the first equation. Do the same procedure for the next pair of terms. Start by converting a sub 6 into a sub 1 plus d multiplied by 6 minus 1, or that is a sub 1 plus 5d. A sub 10, on the other hand, is expanded to a sub 1 plus d times the quantity of 10 less 1, which is simplified as a sub 1 plus 9d. Then, as stated in the problem, a sub 6 plus a sub 10 is 44. So by expanding the equation, we convert them into initial term and difference with a sub 1 plus 5d plus a sub 1 plus 9d is equal to 44. Simplify terms again to have twice of a sub 1 plus 14 is equal to 44. Consider this as the second equation. With two equations of similar variables, we solve them simultaneously. Take equation 2 less equation 1 to cancel out a sub 1. 14d minus 10d is 4d, and this is equated with 44 minus 24, or that is 20. Divide everything by 4 to isolate d, and come up with d is equal to 5. Having the value for the common difference as 5, substitute it in equation 1 to get 2 a sub 1 plus 10 times 5 is equal to 24. Simplify the equation to have twice of a sub 1 plus 50 is equal to 24. Transpose the constant to the right side of the equation to get 2a sub 1 is equal to negative 26. Then, divide both terms by 2 and have a sub 1 is equal to negative 13. So the initial term is already solved. Let's continue solving for the other two succeeding terms using the explicit formula. A sub 2 is a sub 1 plus d times 2 less 1, or that is a sub 2 is equal to negative 13 plus 5 times 1 to get a sub 2 as negative 8. The third term is a sub 1 plus d times 3 minus 1, which is simplified as a sub 3 is equal to negative 13 plus 5 times 2, or negative 3. Example 4 requires a proof that the following binomials are in arithmetic sequence. Once again, to know if a pattern is in arithmetic sequence, determine the common difference. The first step is to convert the binomials into similar variables by expanding each. The first term, the square of a minus b, can be expanded as a squared minus twice of a times b plus b squared. The second term is already in its simplest form. The third term, the square of a plus b, can be expanded as a squared plus 2ab plus b squared. Now we can determine their difference and check if it is indeed common. So starting from the first two terms, we subtract the quantity of a squared minus 2ab plus b squared from a squared plus b squared. Simply change signs to eliminate the parentheses to have a squared plus b squared minus a squared plus 2ab minus b squared. So by collecting similar terms, everything boils down to 2ab. Let's move on to the next pair of terms. So a squared plus 2ab plus b squared minus the quantity of a squared plus b squared. Distribute the minus sign to have a squared plus 2ab plus b squared minus a squared minus b squared. Collect terms to get 2ab. After having the two difference equal, we have proven that the pattern is an arithmetic sequence.